recording. So welcome back, everybody. And yesterday we went through applications of Wick's theorem. We looked at a diagrammatic representation. But what we're going to do today, because now we've been postponing this discussion about Wick's theorem, and now it's time to actually go through the theorem and also look at further examples which link up with the exercises this week. So the theorem itself is actually demonstrated by induction. And the way we are going to set it up is to first remind you of the cases which we showed for one pair of operators and two pairs of operators. And then we saw that we could rewrite that in terms of these normal ordered products and contractions. Then the theorem is not that difficult to show. It's just based on induction. So if it functions for n operators, it functions also for n+1 operators. So let's just go through the things which we need. And when we are done with that, we are going to go back to selected examples and look at also a generalization of Wick's theorem, which is obviously called Wick's generalized theorem, which is also going to make life a little bit easier when it comes to finding the contractions. And we will show that with examples with the exercises this week. So this week, there's a very useful set of relations we are going to derive for transition probabilities and expectation values of operators, which tells us that if we have a given number of single particle states which differ on the Brown-Niket state, then we can actually zero out many contributions to the expectation value or transition probability. But let's now look at the proof for Wick's theorem. Let's just set up this one. So what we did was to show the theorem for one pair of contractions and two pairs of contractions. So what we did then was a case where we had n equal 2 operators. And in that specific case, what we had explicitly was actually 2 operators, A and B. And in our case, this translates into one creation and one annihilation operator. So this could be something like an expectation value of this type here, of A, I, and AJ dagger. And we could rewrite this one in terms of a contraction, AI, AJ dagger, like this, plus the normal order product of these operators. Just let me quickly remind you of these pretty obvious things which you have seen now several times. The way you would rewrite that expectation value, if you look at this one, is actually, so let me just put that one into parentheses. So what we have done now is to use the anti-commutation relation is equal delta ij. And that normal order product, in this specific case, NAI AJ dagger, is actually equal to minus the expectation value of AJ dagger AI of 0. Now, in all these notations here, what we normally write when we write these equations is that we skip the bra and the cat states. This is just to reduce the notational clutter which you can easily end up with. And then just to remind you of this definition here, this is simply given by this expectation value here, which is the one we started with. So in principle, this looks like a kind of clumsy way of rewriting just this expression here. But this is the basis of the Wick's theorem. And just to quickly remind you, as a short repetition here, if you have the true vacuum, then all these other contractions, they are automatically equal to the roundest number you can think of. So the last one here is something we are going to change when we introduce a new reference state, and that will introduce what's called the particle hole formalism. Then that relation will not be zero. But the only contraction which survives is the one which we have here, and that is a delta ij. Now then, when we went to two pairs of operators, so that means that m is equal to 4, then we are constructing an expectation value, a, b, c, d, where these are operators. And what we discussed previously is that all these operations which you see here, we have to have pairs of creation and annihilation operators. If we have an odd number of operators, these expectation values are always equal to 0. Now, it's pretty common to just rewrite this, unless it can be misunderstood, like this. And then, in our case, for 2, this translates into, let's say, AI, AJ, AK dagger, AL dagger. And when you calculate these expectation values, what you will often see is that this case here is often in many textbooks just written out like this. So that's a little bit sloppy notation. And then this can be rewritten as the normal order product. That means all the creation operators are acting to the left and the annihilation to the left, to the right, sorry. So there's a normal order product of these operators. So when we did the contractions manually with the anti-commutation rules, we got a term like that one. Then we had an additional term, which went like the sum over all the possible pairs of contractions. So this is a kind of strange notation, all possible pairs contracted So that means that of these operators, there are two operators which are left uncontracted. We would write this like this. That means that what this actually gives us is something like, so if you do that, this is the same as delta kj multiplied with the expectation, with the normal order product. So let's just write this out because we are going to reuse this kind of notation later. So it's going to be then the normal order product of these two guys which are not contracted. So this term there, this one, is again equal to 0, the normal order product. We have to change these operators, so that gives us a minus. And then we have AL, AI of 0. And this is always equal to 0. So when you have something which is normal ordered, that is always equal to 0. Okay? But what it means, so this guy here is again the same as us having taken the contraction AJ, a K dagger of 0. So this is an expectation value. In that case, this is the only non-zero one if J is equal to K. So when we write this term here, when we break it down into its individual components, this specific contraction means that we have a Kronecker delta times the rest here, which has to be normal ordered. And when we normal order it, we just count the number of times we permute these operators. We get a minus sign. And at the end, we have to calculate this expectation value, which in this case is exactly equal to 0 by construction. Okay. So this is just a kind of notation which makes everything a little bit more compact. But when you break it down, it has a specific meaning. Okay. That sounds okay. And then finally, for the case with two pairs, the only possibility we have is that we have two pairs being contracted. So one is simply the one pair being contracted, and then we have the final one, which is an AI, AJ, a K dagger, AL. And then we just write it in this kind of sloppy way because this is just to indicate that all of them have to be contracted. But then if we look at the relations we had previously, there's only one of these contractions which gives non-zero. So that means that if I take that contraction or that one, that will obviously be equal to zero. So in this case here, in addition to that one, there's going to be this one times that one. These are the only non-zero ones. And when you translate this one back into the different terms, what this one is going to be is a Kronecker delta Kj and a Kronecker delta IL, which then stands for AJ AK dagger 0, and this one stands for 0 AI AL dagger 0. So this is just us breaking down the different terms and what they mean. Now, Wick's theorem is actually based on induction. So we showed by detailed calculations that it holds for 1 and 2 pairs. So let's see what happens now if we add another operator. So let's now assume that we have a chain of operators, and that this chain of operators has been normal ordered. We have a chain of normal ordered operators. And if you think of the expression which we had here for two particles, now for two operators, this is now a chain of normal ordered sets of operators. So this is a chain of normal ordered operators. This is again a chain because when you break it down, what you would have then is this one times a Kronecker delta. This specific case here is just going to be AK, AL plus AI and AJ when we normal order it. So everything which we have here is a chain of normal ordered operators. So we're just making this assumption that we have showed Wick's theorem, which we did for 1 and 2 pairs. And we assume that we have this chain of X, Y, Z up to W. So this is a chain of operator which has been normal ordered. And now what we are going to do now is we need a small lemma, which we're going to prove. And with that lemma, Wick's theorem is just going to follow immediately. So this lemma L1 stays the following. We add a new operator to the right of this chain, of the chain or the previous chain, so which is a chain of normal ordered operators. So what we have then, when we set it up as a normal ordered chain, we have X, Y, Z up to W, and we add an operator omega. Now, this product here can actually be written, and we are going to show that first. And with that, we can then actually rewrite Wick's theorem and prove Wick's theorem. So we have an X, Y, Z of omega, no, W times omega. That's the first term. Plus, and the next term is just the chain or the sum over all the contractions involving this omega. So remember now that when you have a normal ordered chain, there is no point in permuting things because it's already normal ordered, right? So there's a plus here. So let's add that one. So there's a sum over 1. And I'm going to use this kind of odd notation, which we physicists often like, because we add some meaning to it. Like for those of you who have seen the Ising model, there's a way to denote the nearest neighbors, which is sum over. So this is just the sum over all the contractions with one pair of operators, which then involve only this omega plus the other ones. So we're just marking that like this. Now, think now of the following. So the product is already normal ordered. So this lemma is valid immediately if omega is an annihilation operator. Then it's already normal order. If omega is an annihilation operator. Since then, what we have is that n times x, y, z, all the way to omega, is already normal ordered. And if I construct a contraction, A dagger A, so we are now saying that omega is an annihilation operator, and any of the contractions like that are going to be automagically zero. So if omega is an annihilation operator, this is immediately satisfied. So first, because this form here, which we have, this is already something we can write on a normal order form. And the only thing we need to take into account then is in case this is an annihilation creation operator, because this is defined as an annihilation operator. And then using the commutations, the contraction rules, which we have, this is automatically equal to zero. So this is already satisfied. Does that sound plausible? Okay, so the next one, so we assume then that we have assumed, so just let me remind you that we have assumed that the sequence X, Y, Z, W is normal ordered. Just keep that in mind. And we had that because we are using induction, and for n operators, it's proven, and then we need to prove it for n plus 1. So let's now look at the second case. So that is if all X, Y, Z to W, if they all are annihilation operators. If that is the case, then an omega, so this is also a pretty trivial statement, and omega is an annihilation operator. Then this lemma which we have, this L1, is also trivially satisfied. Is trivially. Okay. So that's the second step. So, and you can see that immediately because if it's an annihilation operator and all the other ones are annihilation operators. So the only thing we actually need to be a little bit careful with now is whether this omega is a creation operator. That's the only case which we need to be a little bit careful with. So 3, if omega is a creation operator, this is when we need to do some thinking here. If that is the case, we need to prove the lemma, to prove L1, this lemma here. If all x, y, z up to w are annihilation operators. And the reason for that is that since in case we have creation operators in this chain, then we know that the one single contraction, a dagger of some a of aj dagger, this contraction here, which we are taking in this specific sum, which you see here, the sum over all possible contractions with that operator. If that's the case, this we know that this one by definition is equal to 0. So the only thing which we need to look at a little bit closer now is actually the case with all the operators being annihilation operators. Questions so far, guys? Okay, so let's put number 4 here. So what we're going to do now is we anti-commute. Commute is omega through all these operators. All x, y, z up to omega to get the first term, And then all the anti-commutations which are produced are the second term of the lemma. So we anti-commute omega to get the first term, to get this term which we wrote like x, y, z, w of omega, the normal order term. And we use all the anti-commutations which are produced give the second term. So all the contractions which are produced then which are non-zero. So when I say which are produced, these are the non-zero ones, are produced, give the second term. So let's try to digest this by looking at examples. And then we generalize that to a general chain of operator. Gives the second term. And that second term is the one where we have x, y, z, w with omega, where we now contract it with one of these guys. So let's look at a simple case. So when I'm going to write a number m here, that is the number of operators we have. So if we have m equal to 2, so just to get a kind of a feeling of what is going on here, example, or rather we can use m equal the number of the, so this is m is equal to the number of operators we have in this chain. So suppose now that we are looking at a normal order chain of A1, like that. And we had to be careful now because we said that the case which is tricky is the one where we have the added operator, which is now a creation operator, and the chain of normal ordered operators being annihilation operators. So this would be the simplest possible example we have. So if I write this out and use the lemma, this should now be the normal order product of A1, AL, plus the normal order product of A1, AL dagger with this contraction. So we're just contracting. So this is just a lemma applied to the case where we have just one operator which has been normal ordered. So what we want to do now is simply to watch what happens when we add operators like this. So we saw earlier that if we have this as an annihilation operator, this is going to give us 0. Now, this term which you see when you write it out, this is nothing but minus. So this is this first term, 0 of A1 of AL. No, sorry, AL dagger, A1. Let me just correct it here. So this is AL, A1. So that's the term which you see here. There's a minus sign because we switch or permute A1 and AL. And then we have the next term, which is simply the expectation value of 0 of A1 AL dagger 0. And that term is something which we have seen before. This is a Kronecker delta, delta 1L. So this is the theorem for, or the application of this lemma to the case where we have one creation operator and one annihilation operator. So it's pretty easy to actually see that this applies as well for more than just one operator. So if we take the case with m equal to 2 here, so let's just remind ourselves of that, or m equal, so let's suppose now that we have this chain here of A1, AL. So what happens when I now add an operator to the right here? Suppose I take an A0, like that. What I want to do now is actually to go over to a set of operators where I have 2 in A, B, C, etc. in this set. So in X, Y, C, etc., I started with putting 1. So we have shown that this formula here follows the lemma. Now I want to have another annihilation operator. So what I'm going to do actually is to have the case where I actually want A0, A1 of AL dagger. So AL dagger is the one we want to add, but we want to have this as a chain of operators. So let's see if I do that, what happens. So this kind of a chain of operator is now equal to A0. And then if I'm plugging in what I did on the previous side, I have plus, and then I have N, and then I have the contraction AL dagger. And I'm just writing it like this. Now, if I look at the first term, I can actually write this immediately as N. This is already normal ordered. A1, AL dagger, like that. Plus an additional term, which I can write out as, let me see now, where did I put up my things? Let me see now what I did. Yeah, plus. And then I have my A0, A1, AL dagger, plus N, A0, A1, AL, and where we have this contraction coming in. And if we look a little bit closer at what we have, this is now going to be minus, and then I have M equal to 2 here. So M equal 2, because I have to interchange AL in order to have it normal ordered. So I have to interchange it with A1 and then with A0. So that is going to be equal to the expectation value of 0. And then I have A0, A1, AL dagger. Oh, sorry. I'm just messing this up here. This is the same as AL dagger, A0, A1. So that's the normal order product, which we have set up here. And I have to make 2 interchanges because now I have 2 operators in this chain. Then the next term, which we are going to have, is going to be a contraction plus I will have the normal ordered operator A0 multiplied with the Kronecker delta, delta A1L, plus the last one, which is going to have the Kronecker delta, delta L0 of N normal ordered A1. So all these terms are equal to 0, okay? So if I have now a chain with 2 operators, you see that two operators, which is a chain which is normal ordered, which will be this one. So I took the previous case, adding an operator to the left, to the right, which is a creation operator. If I now act with this one on the same product, I can actually rewrite that one as a chain of two normal ordered operators multiplied with a new one, which then contains the contractions here and the contraction there. So this is what happens if we have a chain of annihilation operators. So keep in mind now that if one of these is zero, then all the contractions will be zero. Okay? So I can generalize that expression to a much more general case. So I could actually rewrite this in terms of general case. Generally, what we will have then is that if I take and multiply this A0 with a chain of these operators, A2, which is normal ordered, up to some AM, and have this AL dagger, which is being added, then this is nothing, it's just going to be equal to the sum of all the contractions, one type of contractions with a normal order product of A0, A1, up to this AM, and with this AL dagger, we have these with these contractions, plus the normal order product of A0, A1, AM, and AL dagger. So it's actually pretty straightforward to see that. And if you want to do more examples, we could now have a new chain of operators where we could take as a further example of this. You could now look at a chain which has been normal ordered with A1, A2, and then you're adding this AL dagger, and then I'm having a new annihilation operator. And this is a chain then which results into the normal ordered chain of A0, A1, A2, and AL dagger, plus the contraction between N, and then I have A0, A1, and then I have A2, AL, plus the contraction between A0, A1, A2, AL. So I will have this one. And finally, I'm going to get the last one, which is N, A0, A1, A2, AL dagger, which is this one. So this kind of simple manipulations actually prove the lemma that if I have a annihilation operator, series of annihilation operators in a normal order chain, and I add a creation operator, this is going to give rise to the lemma, which we have here, which simply states that the set of contractions, so where did I have the lemma here? So if we have a chain of operators here, which has been normal ordered, and I add, and this chain contains only annihilation operators, then if I add a creation operator, I can still rewrite this in terms of the set of all contractions here between the new operator and all the other ones, plus a standard normal ordered form. And you can see that through the examples and also the more general case where we just keep adding new operators, as we did here. We have an operator here which acts on the chain, and then by repeated usage of this one, which we then can collect into this form here, we can then easily show the lemma. Now, when you have that, then Wick's theorem is actually pretty easy to show, because now we want to prove Wick's theorem if we go back, because we have a chain of operator which we know obeys Wick's theorem. But now we are multiplying this with this operator omega. So normally, it's pretty common to skip the fact that this is actually an expectation value, a vacuum-to-vacuum expectation value. So you will often see this written in this more, how to say, loose form, just to save some clutter in the notation. So this would then be equal to, with the lemma, we have the first term, which is just a normal order term, up to W and omega. So this is normal ordered, and we know that when we have a normal order term, that gives us automatically 0. Then what we have is a new term where we have the sum over all contractions, but we exclude this operator omega in the set of contractions. So that means that we would get X, Y, Z, and then we have contractions of the type of one pair, but omega is not included. And then we have, when we use the lemma, so this is the original piece we had, where we simply have added a new operator. But then we have from the lemma, we have that we have 1, but now we are including the contractions with omega. So I would have xi, xyz, w, and then we have the set of all possible contractions with that specific operator. Now we can move on to 2 pairs being contracted. So the next one is what we had originally from Wick's theorem. And in that case, we don't include omega. And then we would have the contractions on n, x, y, z, or w up to omega, but where we now have contractions of this type. And there's a term where we have to add the lemma, and then we need to contract with omega as well. So omega is then contracted with one of these other operators. And this goes on all the way up to the number of operators which we have, which we are going to call for m, divided by 2. And this does not include omega. And then we have all the possible contractions between the pairs. And remember now that if this is an odd set of operators, we have to be careful. If we have an odd number of operators, we will always get 0. So in this particular case, we have everything contracted except with omega, plus the similar sum of m divided by 2. And now we are including omega. So this includes all possible contractions. And finally, we have an additional term. And now I'm getting a little bit lazy here. So we will have a sum over m plus 1 because we are adding an operator where we exclude contractions with omega. And I'm just putting dots here. And then we have finally m plus 1 divided by 2, including omega. And then I'm just writing this in terms of dots here. So everything is contracted. Now, the point is that if m plus 1 gives an odd number of operators, then we know that operators, then what we have then, we end up with an operator which is uncontracted. Then we will always have an uncontracted operator. And that is always going to give us 0, uncontracted operator. So what we are going to have then is something like this, or which is 0, or something like this, which is also equal to 0. When we have an odd number of operators. Now, if you then look at the sums which we have here, if you now think of just a sum over this m, not including omega plus a sum over all possible contractions here where you include omega. This is simply the sum over all possible contractions. Would you agree upon that? So in one case we excluded it. So the one with no contraction with the omega here is the one which follows from the lemma. This is what you would get from what you had before, where you simply multiply in the operator. So the lemma gives us this addition here. And with that, we know obviously that when we sum without and plus the one with, then that simply has to be the sum of all the operators. And that simply means that Wick's theorem, then we have actually a proof of Wick's theorem by induction, where we keep adding operators. We have shown that it works for one pair and two pairs, and now we see that it works for many pairs. So Wick's theorem simply states then that when we write this expectation value, x, y, z, up to an operator omega of 0, which we often just write like x, y, z up to w, when we have used the theorem, the only thing we need to evaluate is just the sum over all contractions, which we write like this, where we then have the chain of operator. This is the only non-zero term which survives, where all the operators are being contracted. So this is the only non-zero. So when we are setting up the contractions, this is an extremely useful result. There is a generalization of this, which is called obviously Wick's generalized theorem, and I will just state it. The proof is actually, it follows the same lines by induction. So let me just state that one, and after the break, we are going to set up examples of Wick's generalized theorem, because that's something which, if we go back to the examples I went through yesterday, I was actually using Wick's generalized theorem because I only took those contractions which were non-zero. So Wick's generalized theorem is the one we end up using at the end when we are performing the different expectation values. So before we set up the theorem, let's look at an example, so which can motivate the theorem. If we now think of a state ij, this is when we use the creation operators. This is given by these two operators acting on a true vacuum. Now, I'm going to introduce the concept of normal ordered operators. So if you look at these two guys here, they are already in what we call a normal ordered form. So we have creation operators and then the annihilation operators, which in this case are not there. So we would call this for an operator which is already in normal ordered form. If I now take the ket side of this one, no, the bra side, sorry, this is actually equal to aj, ai. So this will also be normal ordered. So both of these. And then if I look at the Hamiltonian, which we had yesterday, that was given, and today I'm switching to Roman letters. Yesterday I had Greek letters, but sometimes I use Romans and some other times Greeks. No pun intended. KVRS multiplied with the operator, the creation and annihilation operators, and AS, AR. Now, if you look at this operator as well, we will call this for a normal ordered operator because we have creation operators to the left and annihilation operators to the right. So in the case where we only have the creation operators or annihilation operators, this is by default normal ordered. So this is also what we would call a normal ordered chain of operators. Yeah.
Just the lefter in between the RNS there.
This one?
No, the one right above.
This one?
No, above, in between the expectation value.
There?
To the left.
This is an R, and this is my attempt at an S.
And the one that's, yeah, no.
This is just a V. That's an interaction. Yeah, I have three types of letters, R, S, and V, which actually turn out badly. So let's now just, before we take a break, I'm just going to sneak in 1 or 2 minutes more, because then I wanted to show you what we did yesterday and rephrase that in terms of Wick's generalized theorem. So yesterday, what we did, and this is roughly where we ended, we calculated this expectation value, ij. This is proportional with us taking all the possible contractions of these operators. Now, there was one thing which we said yesterday. Let's now look at these sets of operators, because these are now sets of normal ordered operators. Now, when we use Wick's theorem, we are subbing over all possible contractions, right? This is essentially what Wick's theorem says. However, if you now look at contractions inside this set of operators, which are normal ordered, then we know that these two guys are zero. We know that any contractions which we make inside here is equal to zero by definition. So because if we go back to the rules which we have set up for the definition of contractions, we see immediately that when we now look at these guys here, these expressions, there's only one which gives us a non-zero contribution. So that means that when you look at this set of contractions, which we could set up all the possible contractions with Wick's theorem, as we did here. But then this can actually be simplified now, and this is Wick's generalized theorem, because if you now look at these contractions, or any one of these inside each set of operators, they're always zero. So you can think of this state as being a normal ordered chain of operators. This is a normal ordered chain of operators, and you can think of that one. So when you take contractions within a chain of normal ordered operators, that is automatically zero. So the only thing we need to do then is actually to look at contractions between these guys here, in different chains of normal ordered operators. And that leads to Wick's generalized theorem, which we will discuss after the break, and makes the calculations much easier, as we will see in connection with the exercises this week. So after the break, I'm going to just set up Wick's generalized theorem, and then show you the examples which are relevant for the exercises this week, and see how easily you can calculate expectation values and transition probabilities. So I went deliberately with 5 minutes over time, but that was because I just wanted to motivate the theorem. And then that means we should do 15 minutes, roughly, and take a break, stretch legs. Okay, so let's now set up the generalized Wick's theorem. If you have a chain of operators, which is normal ordered, so let's suppose now that we have up to a given number, and then we have a new chain of operators, which we just label as B1, B2, etc., and they're all normal ordered. So if you look at the examples we had before the break, this is now an example of a chain of normal ordered operators. Contractions inside here, all those contractions will be zero. So Wick's generalized theorem states the following. Generalized. It states that for an arbitrary product of creation and annihilation operators is given by the following set of contractions. So let's just rewrite this. So it states or product of creation and annihilation operators in which the operators, in which some of the operators are already normal ordered, are already in a normal ordered form. Then the theorem we can rewrite, Wick's generalized theorem. Theorem as, and now let's just write it down here. So what we are looking at is these products of operators where some of them, a subset of these are normal ordered. So we have a up and then a new chain here. So this is now representing an expectation value. This is now done A2, B1, B2, and then C1, C2 plus, and the only term which survives here is that we have all contractions between the operators from the different chains. So the contraction can only take place between chains of operators, between operators from different normal order chains. Contractions are summed over all contractions from different normal order groups. Contractions from different groups of operators. And the best way to actually see this is now to look at the specific examples which we had yesterday, and just to demonstrate again that we get the same result which we had yesterday without proof. It's actually not that difficult to show it, and it's intuitive to when you have a chain of normal ordered operators, all the contractions within those operators are zero, in only the non-zero possibilities. So let me just look at an example which we did yesterday and which we brought back before, where we have this two-particle state, anti-symmetrized. So this is the second two-body or two-particle state for fermions. And then we have the PQRS, potential RS, which we don't specify now. And then we have AP dagger, AQ, AS. Calculate the expectation value of this term IJ of HI and IJ. And if we know the full equation, when we translate this one into the formalism we have been defining now, so we're going to have a PQ multiplied with AJ, AI, and then we have AP, AQ, AS acting on zero. And now we mark again, as we did before the break, these sets of operators, chains of that inside each one of these operators, the contractions are always zero. Back the same thing which we did yesterday. We had four possibilities. The only four non-zero possibilities, where we now simply, instead of bringing back everything here, we just look at the operators themselves. AI, AP, AQ, AS, AR, AI, and AJ. Today was this one. And then we have these two here. And that gave us, so this is just a quick reminder from yesterday, due to all the Kronecker deltas. So we got the Kronecker delta. This one gave us a delta RI, a delta JQ, and this gives us a delta IP. So when we then plot back the summation over four indices, and then we have simply an IJ here. And then the other, and only connect different groups of normal ordered operators. So the next possibility was one where we keep this one. And when we did that yesterday, this gave us simply a JI, and then we had VIJ, these contractions, and then we have this one. Now, when we did that, so this had a minus sign due to the equally or pictorially. You can then say that when you look at the contractions and you have a crossing, this the kind of graphical representation of many of these calculations makes it sometimes what kind of signs you should get and what kind of final expressions you should get. So it's from that, and that gives us simply the matrix element JI or VJI, which is due to visible particles and also a permutation symmetry in a Hamiltonian, that this is exactly equal to that term. This contraction, we can have the crossing one here, which then simply gave us minus IJ V is equal to that term. And then we got what we did when we calculated the expect, which we introduced in the first week in the course. So let's now go a little bit for the exercises this week. And you will see that this gives us a very compact way in look like complicated many-particle expressions. So let's now define a general one. And we are going to assume that the basis we have chosen is not necessarily, and I'm just going to write this as an O operator, and I have a 1 here to indicate that this is a one-body operator, reserved for many-body operators. And then if you see lowercase letters, these are the one-body ones, or at most free particles in this course. So this is going to be given by the integral here. There's 1 here, and then I have Q, and then I have AP dagger, AQ. So that's the second. And now we're going to calculate some expectation values. Or we can look at transition. So when I say expectation value, you go from the same state to the same state. And when you then move from one state to processes can represent what we call transition probabilities. So let's now look at this operator and then KL. So we haven't said whether K and L are equal to I and J. So let's set up the generalized Wick's theorem. So this is now the same as a sum of a P and Q. I have P, lowercase operator, looking at the states JI, and then I have the operators AP dagger, AQ, and then I have AI dagger, AJ. We can think of this as normal ordered operators. So we have this as one possible chain. Now, internally here, we know that these guys, if we try to make the contraction, look at all contractions, we are now only going to focus on those contractions, just single out here, just the operators. And this is the common way by which it's done, and you will too much notational clutter. So clearly, one set of contractions you can do now is simply to have AI with P and Q with I. That means that, this was not, I did something wrong here because and this is L, okay. So that's one possibility. And then the only possibility which is left is actually this one. If we, let's look at this expression. So this is going to give rise to JL, I. So we have the one-body operator, and where Q is replaced by K. Now, if you look at this expression, what does it tell us about the two states here? One particle at a time. So what happens now if L is different from J? Determinant here and a determinant here, where the states which are not acted on the Brown-Niket side, this is automagically 0. This is one of the evaluating contributions to a Hamiltonian matrix. So if I have a Slater determinant here, where I'm marking this with a Slater determinant 1, and I have a Slater determinant 2 here, and the only thing is that they differ. So this can be a many-body or more than one single particle state. If that is the case, then this expression is exactly equal to 0. Yeah? Single. So suppose I take this one, and I take the one-body operator, and then I have a different set of quantum numbers, expectation values. If I now use this, this is a transition probability, then there will be a term and 1, but then I have a Kronecker delta 2, 3. So that is one term. And you see now that particle states, you can actually just read off immediately from the expectation values, the set of terms which simplifies the set of more complicated expressions. Interaction theory, which in a certain sense is the simplest possible many-body theory, are simply these expressions here. Then the way you do it numerically, since you can store this find out whether this is 0 or not, is to compare bit strings. So if these bit strings differ by more, so then you can just put in 0 for that specific contribution. So that's an extremely powerful rule, computational point of view, to actually set up the final problem to diagonalize. This is something which we will discuss pretty soon. You will have a list of these guys here. So if this list says that you have, let's say this one, 0, 0, so 1, 0, 1, 0, then by comparing the strings of bits, it simply tells you automatically 0. And you can see that when you do the calculations here. But let's continue, because we have assumed now that I and J and K and L do not necessarily equal each other, okay? So let's just run through the calculation. We have now is an AJ, AI, a P dagger, AL. So the one contraction which we looked at was this one, and obviously that gave us this one. Set up a similar contraction where I contract these two, and then I can keep, careful here, so we have AI. So sometimes it can be useful to rewrite the operators. So we could now have this one going here, and then we could have this one going here. That is a fully allowed contraction, which was delta IK, and it gives us delta Q of L. So when I'm setting it up now, I need to switch. So I need to switch this one with AP, and also need that one, so at the end. So we are going to get a matrix element or an integral of the operator, and where I now have A. So if I look back at the states, which I'm setting up, so I have an IJ, and then I have acquiring now, is that I has to be equal to K, and obviously J and L do not need to be the same. So if this is an eigenbasis of this operator, then J obviously has to be equal to L. Quantum numbers, which is not participating in the calculation or in the operation of the operator, ket side. So for one body operator, if the states on the Brown-Ket side pays by more than one type of single particle states, which is not included in the operation of the operator, actually equal to 0. Now you have two more sets of contractions which you can set. You could actually have AI going to AK here. That's another possibility, but we already had that. If I do that, if I take AI going to AK, then the only option I have is AJ going to A action within the operator. So the only possibility you have here is actually the possibilities where you contract one of these with these operators and these operators, and try to set up these possible contractions and convince yourself and get. And that puts a limit or constraint on the states which are not acted upon by the operator. Okay. The next example, which is also in the exercises, then we have a two-body operator. So let's now IJ, and now we have an operator, general two-body operator, and we don't specify what that looks like. And then we have the same states K and eta self to the operators only. We are going to have something which looks like as we had before, AQ, AL. So if I do that, then obviously the thing I must have is either these two going, that's one of the contractions. I can set of contractions. Then I can have the next one, the operator, previously where the two-body operator was given by the Hamiltonian, the two-body Hamiltonian. And then we could have this one, and then with this set of contractions with just the same one as we started with. So the one which we have here is going to give rise to IJ, the operator, which is a two-body operator. And then I have K minus JI, the two-body operator, KL. This term is going to have a plus KL, now LK. And then finally, here we're going to have minus IJ of O2 of LK, two-body operator. Now let's get a little bit more ambitious and try to see if we can say something about, so in this particular case, for the one-body operator, we saw now that if the slated it states, but I should add not acted upon by the operator, then clearly this is here that 2 and 3 is one specific contribution where we have a Kronecker delta 2 and 3. If we then move to the two-body, suppose we have a three-body state. So we define now a state, and let's just put labels 1, 2, 3, like that. And there's A1 dagger, A2 dagger, A3 dagger, acting on 0. And then we have another state, 4, 5, A5, A6 of 0. And now we calculate the expectation value of 2, 3. And then I have this two-body operator of 4, 5, 6. So in this specific case. So one of them, we're just putting it up, is A2 operator, EQ. And then I have A4, A5, A6. Up these two guys, no, not those guys. I can take these two and do the possible set of contractions with these. I contract this one and this operators. And the other one is when I take this one. Similarly, what I can do now is to take these two operators and team them up with them. These, when we look at this set of contractions, let's just single them out like this. This will now two-body operator, and then for 5 minus, and this is as we did before, of 0254. Condon-Slater rule. We looked at it for a one-body operator, but if you now look at this, you see that this requires that we have delta 3 6. So state 3 has, so what you can say now, if a Slater determinant differs on the ket side and the brides, this is automatically equal to 0. So what we can do now is to sum this. If we have 2 Slater 1 and SD2, and we now calculate an expectation value with this two-body operator of SD2, this is 0 if SD1 and SD2 differ by more than 2 single particle states. So this we have also additions to this in case they differ by 1 single formula I want you to derive in the exercises. And if they are the same, this is something we have, let's say a Slater determinant here, which we just call 1, and we do the expectancy 1. So these are the same states now. So one of the things you're going to see then, in case you have many states, this is going to be equal to 1/2, and then you sum over all the single particle states up to the number of ij, the operator, the two-body operator, ij here, minus ji, and then the operator, and then ij. Value of the ground state ansatz. This is something which we did in the first weekend, the second Slater determinants. We end up with this expression. If we have only then the expression is pretty simple. Then we have a Kronecker delta. No, sorry, only two single particle states which differ, only 2 which differ. Then you will see that you will get a term I'll show in the exercises is what happens if you have only 1 single particle states which differs. If you have 2 states which are different, here we are enforcing that 3 has to be equal to Z side. It's automatically 0. So what you get then are analytical expressions which use the Hamiltonian matrix for a diagonalization algorithm. So Wick's theorem allows you to set up this compact way, and you can see very quickly from the contractions here that in case which are different, and you have a two-body operator only, which acts on 2 at a time, then this has to be 0. And we want to see whether this gives non-zero or something which is 0, which make up a given Slater determinant. And as I said here, you can actually make a bit comparison. And if they differ by 1 or more, it's automatically 0. And then you don't need to do anything. Okay, I think it's okay to going to redefine the vacuum in terms of what's called a particle hole vacuum. And that if we were to have 10 single particle states here, then we would have to look at the contractions an operator, which is a two-body. And this is something which we can rewrite in a more compact way using the particle hole formulas and have rules which we can use on more complex cases, which at the same time give us exacted and boring calculations. Okay, so I wanted to give you some hints in connection with Slater rules of things which we are going to use when we start with one of our many-body methods, which is called full configuration interaction theory. You want to do the exercises here, we can do that. And if you want to do them in your offices or back at home, it's obviously, but okay, guys.